Imagine the ultimate cosmic cold case. We've got all the evidence of what the universe looks like today, right? But the exact moment of the Big Bang? Well, that file has been totally locked. It's corrupted by this massive mathematical glitch that physicists have literally been banging their heads against for decades. Welcome to this explainer, where we're going to try to crack this case wide open and actually look at the math of creation itself.
Okay, so let's dive right into some breaking news from the astrophysics world. We're looking at a huge new paper titled Ultraviolet Completion of the Big Bang in Quadratic Gravity. It's by researchers Rulin Liu, Jerome Quinton, and Nayesh F. Shorty, and it was published by the American Physical Society. Honestly, this is a massive deal, because this team might have just figured out a way for us to look directly at the beginning of time without all of our physics completely breaking down.
So to really grasp the problem they were up against, we have to talk about the singularity. You've probably heard the term. It's that absolute starting point of the universe, a point of literally infinite density where our standard laws of physics just break. They stop working. Think about Einstein's theory of general relativity like it's a perfect, high-definition camera. It takes incredibly pristine pictures of planets and stars and galaxies. But if you take that same camera and point it directly at the intense, infinite heat of the Big Bang, the lens just completely flares out and shatters.
And that is where we get to the solution. We basically have two competing ideas going head-to-head here. On one side, there's Einstein's general relativity. As we know, it works beautifully late in the universe's life, but it completely fails at the very beginning. On the other side, we have the researchers' proposed new tool, which they call quantum quadratic gravity, or QQG. You can think of QQG as a highly specialized new camera filter. It's specifically designed to work perfectly at that absolute beginning, at infinite density, and then, importantly, it smoothly transitions the universe back over to standard general relativity later on. So here is the absolute crucial takeaway. At the exact split-second moment of the Big Bang, general relativity doesn't even exist yet. It's just pure QQG. There's zero general relativity happening at infinite density. Honestly, this is the single most important insight from the entire paper. Instead of trying to force Einstein's broken camera to work in an environment where it just can't, these physicists are suggesting that pure quantum quadratic gravity handles that infinite density flawlessly.
Now, the actual mathematical engine behind this early time period is pretty intense. And don't worry, we are absolutely skipping the deep math today, but the core calculation here is what actually solves that singularity glitch. The math proves that, in the extreme chaotic environment of the early Big Bang, gravity actually acts differently. It effectively weakens at microscopic distances, which entirely avoids that infinite crash that usually ruins standard physics.
What's really cool is how this new math builds into a super elegant three-step timeline of our universe. Step 1, we start off in pure QQG at extreme density. Step 2, as the math of the universe dynamically shifts, it naturally triggers something called cosmic inflation, which is basically the massive, incredibly rapid expansion of the early universe. And then step 3, once that inflation ends, QQG just gracefully hands the baton over to general relativity, and physics as we know it takes over to create the standard radiation era we're living in today.
But you might be wondering, why does this matter right now? Well, for a long time, the leading idea for the early universe was something called Starobinsky inflation. The problem is, our absolute newest, best telescope data is actually starting to poke holes in it. The researchers specifically note that standard Starobinsky inflation is in slight tension with new observations. Basically, the actual universe we're observing out there is pulling away from the old math. It was creating this huge mystery that desperately needed to be solved.
And that brings us to the real smoking gun of this paper. When you plot out the sweet spot of the actual data coming in from our latest telescope observations, the old Starobinsky theory sits uncomfortably outside of it. It just doesn't quite fit anymore. But this new QQG theory, it acts like the perfect lens filter. It brings everything perfectly into focus, landing smack dab in the middle of the viable window of what we are actually observing in the real universe. It's an incredible match.
And what makes this paper incredibly powerful is that it isn't just explaining the past, it's actively predicting the future. The team calculated a very specific hard number for something called the tensor-to-scalar ratio, which is represented by the letter r. They predict that r has to be greater than or equal to 0.01. To put that simply, this gives future astronomers a highly specific gravitational wave signature to go out and hunt for. If we find that exact signature, boom, it's massive proof for this entire theory.
Now, I want to be completely honest with you here because we're looking at the messy reality of the scientific process, right? There are definitely caveats. To actually make this beautiful math work, the researchers had to assume the existence of over 100,000 matter fields in the early universe.
The theory also hits what they call a mathematical strong coupling limit right at the moment when standard physics takes over. Basically, that just means they need to do some further, really rigorous mathematical stress testing to make sure the equations hold up perfectly during that transition phase.
But even with those lingering questions and extreme assumptions, there is a viable parameter space where the math works beautifully. Within a very specific, testable window, as long as those matter fields exist, the theory remains completely mathematically controlled and it perfectly matches our reality. And that means this investigation is very much alive.
Which leaves us with the ultimate question. What will the next generation of telescopes reveal? We literally have the blueprint now. We know exactly what gravitational wave signature we need to look for. Will the upcoming telescope data prove this eccentric, genius blueprint right and confirm quantum quadratic gravity once and for all? Keep your curiosity burning, because the ultimate cosmic cold case might actually, finally, be on the verge of being closed.